We'll be studying the relationship between voltage and equipotentials. In the previous video, I defined the concept of electric potential. The change in electric potential, delta V, is given by the change in the electric potential energy per unit test charge Q. Now, the definition of voltage also inspires us to give units for it. The units of voltage are named in honor of the famous scientist Volta, the Italian scientist Volta, who made the first battery. So volts are equal to, the units of energy are joules, divided by coulombs. So that's the basic unit of electric potential. Volts is abbreviated capital V, so capital V equal to J over C. Then we also studied in the previous video how to find the change in potential energy if we are given the electric field everywhere. Now this procedure will be carried out for many examples in the future videos, but right now let's assume that if the electric field is given to us, how do you find the voltage? It's got by simply taking any path between the initial and final points and integrating the electric field at every point with the dot product of the displacement vector at that point, and that's equal to the negative of the electric potential. The last thing we saw in the previous video was how to find the parallel component of the electric field. That's given by the change in voltage over the change in displacement along the parallel component with a negative sign also. Now this last, either of these two equations can be used to get new units for the electric field itself. The electric field is given by, in terms of voltage, as volts per meter. Actually, most professionals use this definition. Now, volts per meter is of course also the same as newtons per coulomb, which you've been using so far. But if you look at any journal or any handbook, electric field is always measured in terms of volts per meter, which goes to show that voltage is a very important quantity in E&M. So once you have this, these concepts, what else can you do? The next thing we're going to look at are called equipotentials. Equipotentials are lines of constant potential. So here I have a hill, think of it as a mountain or something, and I've drawn contours. So a geologist would look at the contour map of a hill. Now if I did not draw this three-dimensionally but drew it two-dimensionally, then if I saw this from above, I would get a picture that looks like this. As you can see, the left side contours are going to be squished together, while the right side contours are going to be somewhat spread out. Okay, that actually reflects the fact that the left side is steeper than the right side. So if you look at a 2D map of the mountain, then if you're an experienced hiker or a mountain climber, you know immediately that an easy hike would be to start from here and go along the path indicated by the largest contour gaps. Okay, that would be an easy hike. A moderately difficult hike would be something like this, where contours are getting squished a little bit more. And the hardest hike would be this one. So it's pretty clear which hike you should do depending on your ambition or skill level. What you're seeing here is a phenomenon of bunching. The change in voltage over the change in distance, here you're getting the same change in voltage. Now the difference between these two is a change in voltage. The change in voltage is the same, but the distance over which it occurs is smaller. So this has a bigger field and that has a smaller field. So the magnitude of the electric field can be found by the bunching up of the equipotentials. Okay, so that is one of the important insights you can get by these contour maps. The other thing is the change in voltage is negative if you go from a higher voltage to a lower voltage, or if you climb down a mountain, your gravitational potential energy decreases, so your number of joules drops. So in the same manner, if you go down along this contour, you're going to lose voltage, and that also gives us the direction of the electric field. So the direction of the electric field is precisely going to be given by going radially outward from the top of the mountain, and it basically gives us the direction in which a particle would most rapidly descend. It's called the steepest descent. I'm going to now talk a little bit about some properties of these equipotentials. These surfaces of constant potential are called equipotentials. Now in this example, equipotentials are closed lines, but remember this hill is two-dimensional because I drew it on a piece of paper and gave it a third dimension by drawing circles like that. If I drew this thing in 3 dimensions, the equipotentials would be a closed surface. So they are actually closed surfaces. Although they look like lines in this 2D plot. So what are the properties of these equipotentials? Now in electricity, we'll be concerned with conductors. So let's draw a conductor. Suppose I have a piece of metal, hunk of metal, and let's just draw a cavity also inside it. I'll put the metallic shading on it. The first thing I want to tell you is that on the metal surface, the entire conductor is one potential. So if I touch it with a battery with some potential V, then regardless of how crazy the surface looks, for example, it's got a small bump there and all that, it doesn't matter. The entire surface will have the same potential. And the reason behind this, the first property, let me write that, entire conductor had one potential. The reason for this really has to do with semantics, because if the conductor was not at one potential, if there was a place where the potential is V1 and another place where it's V2 and V1 is less than V2, then the potential energy will also be different in those two places. Now, as you know, nature always prefers a point of lower potential energy. If you leave a ball here, it will come down. So if you have different potential energies on the surface of the conductor, then charge is going to start moving from the higher potential to the lower potential. There's going to be a mass migration of charges, and that will lead to a violation of electrostatic equilibrium. So the electrostatic equilibrium assumption rules out any such movement, and so we are forced to conclude that the entire surface must be at one potential. The second property is quite a remarkable property, and that is electric field lines are always perpendicular to the conductor. Why is that? What I'm trying to tell you is this. If I have field lines, they will always terminate. So let's suppose lightning hits this conductor. I'm saying that the electric field lines will always be at 90 degrees to the conductor. Now, why is that the case? Suppose that's not the case. Let's suppose, for the sake of argument, that you have a field line that is not at 90 degrees. So it's going to be at some weird angle like that. We can break it up into two components, the perpendicular component, which I'll call E perpendicular, and a parallel component, which I'll call E parallel. You can probably already see where this argument is going. If I have a small test charge here, then because of the parallel component, it'll scoot along the direction of the conductor. But if it moves along the conductor due to the electric field E parallel, it must accelerate because F equals QE equals MA. So F equals Q times E parallel equals mass times acceleration along the parallel direction, means that you're going to get acceleration along the parallel direction. But that violates the first principle, which is that the entire conductor must be at one potential, because acceleration is only possible if this electron is trying to get from a higher potential to a lower potential. But we've already said that the entire conductor is at one potential, so you cannot possibly have the E parallel component. Another way to look at this argument that you cannot have E parallel is to simply look at this equation. E parallel is equal to the change in voltage over the change in displacement. If I had a change in voltage, that will again violate the first principle, because it says there is no change in voltage on the surface of the conductor. The third principle, which I've already touched on, I'll mention it again, and that is electric field always goes from a higher to a lower potential. I'm going to take this opportunity to tell you something more general than this third equation. That third equation looks like it's trying to be a derivative, okay? But it's a derivative in some strange direction, del S. So there is a concept known as a partial derivative, which is really useful to make that equation more rigorous. So according to that equation, I'm going to write the electric field as negative. Now I'm going to replace that with something called the gradient of the voltage V. Now what this gradient really means is it is equal to some I hat times the derivative with respect to x of the voltage plus j hat times the derivative with respect to y of the voltage plus k hat, the derivative with respect to z of the voltage. Towards the end of week 4 notes, you will see some examples of how to get electric field in 3 directions from voltage, which is just a scalar function. Remember, voltage is just a function of x, y, and z. So from a single function, you're able to manufacture 3 separate functions, which are the x, y, and z components of the electric field. So negative I hat times del by del x v is the x component of the electric field. Negative j hat times del by del y of the voltage is the y component of the electric field. And negative k hat del by del z of the voltage is the k component of the electric field. Now that's a more rigorous equation than that, because that's just an arbitrary direction you're making up, whereas this gives us the directions in a very concrete manner. Just to take an example of this, let's suppose you have the potential V to be given by the following function. Let's just take the potential V to be given by V of x, y, z to be ax squared plus bxy plus cz. Okay, I just made this up right now while I was writing. So what would the electric field be of this potential? Let's find the x component. Ex is going to be negative del by del x times v. Del by del x times v means I take only the derivative with respect to x and keep y and z constant. If z is constant, this does not contribute. So I'm going to get negative 2 times ax. The second term, I'm going to keep y constant, so that just gives me plus by, and the third term is 0. So I have the x component. The y component of the electric field is negative, by this equation, is negative del by del y of v. Now the first term does not have a y, so that's just going to be 0. The second term does have a y, so b and x are treated as constants now, so I get bx. And the third term does not have a y, so the electric field in the y direction has got components negative bx. The last thing I need to find is electric field in the z direction, and that is negative del by del z of this same thing, same quantity v. The only term involving z is the third one, so that's just negative 0 plus z. So the electric field in the x direction is actually changing with position because it depends on both x and y. The electric field in the y direction also changes with position because it depends on x, while the electric field in the z direction is a constant. It does not change with distance.